Hi, everyone. Thank you for joining us this afternoon for the virtual lunch discussion with CSAIL's Polina Golland. Professor Golland will discuss recent work from her group, including building machine learning methods that learn joint representations of images and associated text to improve image-based clinical decision-making. Please send me any questions for Polina in the chat, and I will ask on your behalf at the conclusion of the talk. With that said, please take it away, Polina.
Great, thank you, Matt. Good afternoon, everybody. I want to share some of the work we've been recently doing in collaboration with Peter Solowitz's group and our colleagues at Beth Israel Deaconess Medical Center. Giedicke and Ray are really the two lead authors on the paper we recently published, and they're students in CSAIL. So to give you a sense of the problem we're trying to address, we are looking at a particular clinical condition called congestive heart failure. So what happens in heart failure is that the heart stops being as efficient as it could at pumping the blood through the body and the brain. And if that happens, then the blood pressure builds up because basically the pump is not working as well. And the first immediate effect of that is that the fluid from capillaries in the lungs seeps into the airspace in the lungs. And so this can be seen almost instantaneously in chest X-rays. And chest X-rays are used as sort of one of the first diagnostic tools when somebody comes into emergency room and complains of shortness of breath. So on the picture on the left is one of our collaborators, Stephen Horn, and the patient. And basically, Steve is an emergency room physician. And so when he gets a patient who complains of shortness of breath and chest X-rays taken, effectively, there are several decisions that have to be made under pressure of time. And these decisions have to do with whether to admit, they have to do with the path that this patient will take through the hospital system. So one option is to prescribe medication and send the patient home if there is a sense that actually this is something that will resolve fairly easily on its own, or admit them to the hospital if there is a suspicion that this is something that requires longer term care, or admit them to emergency room where the patient might stay for a few hours and then be sent home. So then as the patient stays in the hospital, chest X-ray images are taken at intervals of time, probably once a day or even more frequently if there is a need to monitor the fluid status in the lungs more frequently than once a day. And based on what the physicians see in the images, they adjust medication to treat the patients. And finally, when the patient is discharged, there is a belief in the medical community that their lungs should be completely dry, is the term, meaning that this phenomenon of fluid accumulation in the lungs should have resolved. Otherwise, this patient is very likely to come back to the hospital within a short period of time because basically they haven't been stabilized enough. Okay, and so this is what chest X-rays are being used in the context of heart failure. Unfortunately, right now, the situation is such that, well, so images are great because you can look at them and you can see the phenomenon you're interested in the images. So in some sense, we use our visual system as part of the diagnostic pipeline. Unfortunately, this also means that in order to understand how this patient reacted to medication or resolve or what their lungs look like in previous visits, since heart failure is a chronic condition, you again have to look at the previous X-rays, which usually means that nobody does, and the images just sit in the archival systems without contributing potentially valuable information to the future visits and the future encounters with the same patient. Moreover, studies of efficacy of treatments are made difficult if the final outcome is buried in the image. So it's implicitly captured in the image, but if somebody has to look at every image, it's quite impossible to run, for example, statistical analysis about which medication or which sort of clinical workflow improve the patients better, so faster or with better long-term outcomes. And so both of these problems require taking the images and extracting quantitative measures of how much fluid there is in the lung. And that's exactly what we're going to do in this project. So as you can guess, our initial attempt was to train image classifiers that take images as input and produce a numerical score between 0 and 3. And so I'm listing clinical terms for these levels, but effectively you can think of it as a progression from 0 being no edema at all to 3 being fairly severe amount. Now, I want to talk you through sort of this project and how it developed. So to start with, to train a classifier, you have to have a lot of examples of images and labels. So in our case, it would be level of edema severity. The problem is that there are no numerical labels. Remember, that's how we started here, that we don't have a good way to extract the numerical labels. But what we do have is radiologist reports. So this is free text that the radiologist wrote down when they examined the image. Our work is grounded in a very large open source image data set called the MIMIC. So MIMIC is a much bigger database than just images. It's basically a database of physiological signals, images, radiology reports, doctor notes, everything there is to know about patients in emergency room and intensive care units at Beth Israel Deaconess Hospital that was created, curated, and released to the scientific community for research. So, so the numbers here give you a sense of the size of the data set and give you examples of images and radiology reports that we might have to work with. So we have about 250,000 chest X-rays, and these chest X-rays represent about 65K patients. The heart failure cohort, if we constrain ourselves to just heart failure cohort, the numbers go down by an order of magnitude. We have built a bunch of software tools that are using regular expressions to find relevant clinical keywords. And through that, in collaboration with our radiology colleagues, label about 3,000, somewhere between 3,000 and 7,000 images, depending on the instantiation of this model. And finally, we have the gold standard image set where 3 radiologists examined the images and arrived at consensus for the labels. So clearly we can't use this gold standard data set to train anything, it's way too small, but we will use it to evaluate the methods. So the idea here is that we label the images using regular expression keyword matching, and then we'll evaluate it by matching it to radiologists, comparing it to the radiologist consensus. And so you can train a classifier and evaluate its accuracy, and it turns out it's not good enough. And so what I will show you today is our work on how to bring this to the level of accuracy that would become acceptable in terms of clinical practice. And in particular, in the next 3 slides, I'll show you sort of the architectural innovations that we're doing. This work, I have to say, is inspired by computer vision and natural speech understanding projects in CSAIL. Some of the ideas we got by watching actually Jim Glass and his students talk about understanding how people talk about images in a completely unsupervised way. So our problem is supervised, but we took inspiration from their work. So let's see. So I have my classifier, and so I'll split it apart into sort of the encoder part and the classifier. And the classifier takes an output of the encoder. So you can think of it as an intermediate layer representation and builds the classification model. And typically, so this is sort of classical classification using deep nets. We will have a loss function that penalizes errors, and by adjusting the parameters of the classifier to minimize the loss, we hope to get good accuracy. And as I said, we've discovered that this is not good enough. So here's the architecture that we actually ended up implementing. And so the idea here is that text contains much more information than the keywords that we are searching for in our attempt to label the corresponding images. So instead of just throwing away all this information, we will use it. And in particular, what's going to happen here is that both the images and the text, through the corresponding modality-specific encoders, get mapped into the joint space. This joint loss function encourages the representation of images and the representation of text from the same imaging event, so same patient, same time, to map very close to each other. And it encourages images and text that are mismatched, either different patient or different time of the imaging, to map far away from each other. So our hope is that by putting this loss into the training of this model, we are creating some latent representation that actually represents the relationship between images and reports. And finally, the classifiers for both image and radiology reports are connected to the classical classification losses. So the system is trained together, meaning that the classifiers and the embedding and the encoders are trained together. And so the classifiers are encouraged to perform well on a task at hand, meaning to classify labels or radiology reports, while encouraging the structure in the internal space, in the space that represents both images and reports. And so we have experimented with, so the original version, the preliminary version of this work was presented at McKay in 2020. And since then, we've developed a method that also enables us to look at the relationships, not at the level of the whole image and the whole report, but at the level of regions in the image and sentences in the report. So there are a couple of variants of the model. As you can imagine, I wouldn't be giving you this talk if it didn't improve the accuracy. And so by any measure that we've evaluated the model, it does much better than the baseline model. Let me go back to the training. I should say also that at inference time, we remove all of the structure and in fact only deploy image encoder and image classifier to classify a new image. Now, let me go back to the training example. There are two reasons why this model performs better than the baseline model. One of them is that this joint loss ties the two representations together. And it turns out that classifying radiology reports is a much easier task than classifying images. To give you a sense of performance, basically, our accuracy in classifying images without doing anything sophisticated with the baseline model is about 75%. Whereas the radiology reports can classify it as accurately as 90% accuracy. By tying these two representations together, effectively, we have the radiology reports drag the images into the right representation. So the representation of images gets affected by the representation of radiology reports, and that improves the accuracy. But it's more than that. Remember that how the numbers of available training data dropped by an order of magnitude when we went to label data. Sorry, when we went to heart failure cohort, and then for another order of magnitude when we went to label data. And so again, we realized that it would be pity to have all those images lie around and not contribute, the images we couldn't label. And so what's happening here is that the joint loss can be trained based on unlabeled image report pairs. Yeah, I don't need to know what the severity of the pair is to impose this constraint that if the image and the report match, meaning they come from the same imaging event, they should map close to each other. And if they're mismatched, they should map far away. This idea actually is related to contrastive loss in computer vision, for those of you who are wondering about that. And so what's happening here is that not only we're taking advantage of the fact that radiology reports are easier to classify, we're also learning this joint embedding based on much more data, 2 orders of magnitude more data. And the result have better confidence that we're actually learning a good representation for the images. And so this is what the 3 bars show. The image only shows results for 3 different scenarios, basically, for fully supervised image only model. The joint supervised is the one where we train both on images and reports, but all of them are constrained to be labeled. The semi-supervised approach says I can learn the joint representation from all of my data, and only the training of the classifiers requires the label. And so we see that basically it improves the accuracy even more. Okay, the nice side effect of this model is this ability to visualize what the model is doing. So for those of you who have done machine learning, know that GradCam or something like that is very commonly used in computer vision to highlight the part of the image that contributed the most to the decision of the classifier. Well, it turns out it's a completely useless model for medical image analysis. I'm exaggerating, but only a little bit. So the challenge with models that highlight the part of the image that contributed mostly to the classifier in medical imaging is that, well, so let's run through the thought experiment. Suppose I have a patient whose lungs are congested with fluid. If my classifier is doing its job right, then when I ask which part of the image was affecting the classifier the most, it should highlight the lungs. Now, suppose I have a patient who doesn't have any fluid in the lungs. What should this model highlight? Well, clearly the lungs, because to understand whether there is fluid in the lungs or not, it should look in the lungs. So this approach to figuring out what the model is doing is extremely useful if you're trying to figure out where the object is in the image that affected the decision. But it's not that useful if you're trying to figure out what the difference in texture was in that part of the image. And so we've been kind of toying with ideas of how to capture these differences. Well, it turns out that this model gives us a very nice connection to text, and as a result, a way to visualize important differences. And in particular, what I will do is I will take that joint representation, and instead of highlighting parts of lung, as you can see on the left, or in addition to highlighting parts of lung, I can also highlight sentences or words in the text that triggered the decision or affected the decision the most. And at least sort of anecdotally, by showing this to our clinical collaborators, it seems like there is a lot of evidence that this is a very useful model. We are currently investigating further directions of further research into providing supporting evidence for models like this. Okay, and so this code runs at the hospital, and sort of one of the visions that we have for the project going forward is some sort of visualizer that tracks the patient status that will include not just image-based classification, but also the medicines that were administered, the tests that were done for this patient, so that at one glance, the treating physician can understand how fluid congestion in the lungs has been escalating, resolving, whether the patient is ready for discharge, and so on. So to summarize, what I showed you today is one example of the style of work that my group is doing. We're motivated by a real clinical problem where we've built a neural network model that learns joint representation of images and text. Unlike much of the supervised and unsupervised work in computer vision and speech and language understanding, we're using these joint representations to improve the quality of the classification. The nice thing about this is that the radiology reports, well, so basically one of the challenges is that the radiology report is not available at the time when we apply this to a new image for a new patient. However, because they're available during training time in this very large data set, we can utilize the relationship between the radiology reports and the images to improve the classification. And as I already mentioned, effectively, we get a substantial boost by looking at all of the data as opposed to just the data that we could label. And our current work is both pursuing further methodological development as well as thinking about how to integrate this into clinical workflow and ultimately help the physician make the best decisions for every individual patient. Thank you.
Thank you so much, Polina, for a great talk. We do have a few questions, if you don't mind.
Not at all. Great.
So one question I received, do you think AI in healthcare requires a revolutionary path or an evolutionary path?
Oh man, I don't do philosophy that well. I think so. So I don't think, sorry, I might say something that will get a bunch of my colleagues upset, but I don't think AI in healthcare is a topic or a field. There is healthcare and there is doing research to help physicians treat patients. So I should say that my group has done quite a lot of work that has nothing to do with machine learning and yet analyzes images in a ways that bring the day closer where physicians can fully utilize information in the images. So I think what has to happen, and so by one standard, it's a revolution. By another, by somebody else's measure, it's just incremental progress. Is that right now there's quite a bit of a mismatch between the methods that are developed in the machine learning community and the problems that need to be solved in the clinical world. So I think. And so because I think that, my group basically is working to bridge that gap and work on either recasting clinical problems into frameworks that can be addressed with existing algorithms or develop new algorithms that match the problem. So quite often what happens is that this mismatch precludes the most recent innovations in AI or any other computing field to be integrated into the clinical world, because the problems are just a little bit different. And so I think it's important for us to think about formulations that connect between the problems and the algorithms.
Awesome. Thank you so much for that. Another question I received, how do you solve the problem of X-ray data ownership?
Oh, this is a great question that I've definitely struggled with a lot. So we don't resolve it at all because we work with this amazing team of physicians at Beth Israel Deaconess Center. So BIDMC decided it was going to be different. And instead of being cagey about their data, what they've done in the last several decades is they curate the data, they anonymize it, and they release it to the scientific community for doing research. And so we don't resolve the issue because we're given the data as part of PhysioNet or Mimic. Those are the two keywords for those of you who are building machine learning methods and are looking for data to play with. So my approach overall in research, not in this, so in some sense, this project is great that way, right? The physicians gave us the data, but in some sense, they gave the data to the rest of the world as well. So in my overall research, I work with physicians who understand the benefits of bringing together interdisciplinary teams, and they resolve the ownership issue by running studies where there's patient consent and then sharing the data with us. So I would say that it's sort of like, I would say that it's one of these things where I resolve it by only working with physicians who give us data.
Yeah, that sounds good. Thank you for answering that. Another question I received is if you could speak more to current efforts in data collection and alternatives to manual labeling.
So I'm suspecting that the question is not really data collection, because images are acquired every day in magnitudes that are unimaginable to us in a hospital, but rather it focuses on this problem that many supervised methods require every image to be looked at by human and annotated in a particular way. So either do segmentation or say this is severity level 2 or something like that. And so the efforts that I know about, well, so there are several kind of different fields of different subfields of medical imaging have it easier or harder. So for example, in some fields like mammography, the label that we would want to get out of the images is recorded as part of the clinical practice. So I told you in this talk that we are working with data where the radiologist wrote the description down, in mammography, the radiologists are forced by effectively a professional body to record a number that indicates what they think about this case. And so this is a particularly ripe area for machine learning research because the labels available are generated as part of the clinical practice. This is the only field that I know of where it's done routinely for every image acquired. Then I know of a couple of startups that are developing platforms that enable people to annotate them more easily. One of them is a spin-off from MIT, Centaur Systems. Their idea is recruiting radiologists to label images effectively. I know that many commercial entities, such as startups trying to solve very specific application, end up effectively training labelers and annotating them. I have to say that I'm kind of sad not to see a lot of research in the area of how to speed up annotation. I've seen a couple of interesting works, but so far, basically everything I know when you want to do it at scale is done either algorithmically like we did it in this project where we extract keywords to label, or it is done manually by people looking at the images.
Thank you. And this next question might be another philosophical one, but I'm just going to throw it out to you just in case.
Sure.
Do we aim to decrease the number of doctors in the field, or do you think that we aim to improve the decision making?
I think neither are worthy goals. These are wrong goals to have. What we should strive for is better care for the patients. Right, so in some sense, I'm refusing to worry about what the optimal number of doctors is. That's for the guilt, right? This is for the medical boards to decide. But in some sense, I don't think it should be decided top down. I think we should be improving quality of care. So not even decision making, not even diagnosis, quality of care. So in some sense, we should be focusing on not just extracting actionable information, but also acting on it in ways that improves patients' care. So we're doing our bit by improving diagnostics. But then again, these diagnostic numbers need to be integrated into the clinical workflow so that the patients can benefit from improved diagnosis. And this is, of course, from a computer scientist who works in between these two fields. I'm sure that the doctors will have a different opinion about this.
No, I think that was a great answer. And I know we're coming to the top of the half hour, and I got everyone's questions out. So I wanted to say, I guess, thank you, Polina, so much for joining us.
Thank you for having me
this afternoon. Do you have any final words for the group, or?
So for the graduate students kind of thinking about where their research goes, I want to encourage them to, again, think about how formulations of the problems can change the path you take towards solving it. And so thinking about formulations that connect to contemporary problems is a good way to make sure you invent algorithms that have hope of being used.
Awesome. Thank you so much, Polina, and thank you everyone for joining us today.
Great. Have a great afternoon and the weekend, and thank you for joining, everybody.
Thank you, everyone. Have a good day.